Here in this video we're going to take a look at indefinite integrals using u sub of exponential and ln functions. In this first example I have the integral of x cubed e to the 4x to the fourth dx. And if you look at the two polynomial pieces, we have an x cubed here and a 4x to the fourth. So if we took the derivative of x cubed, we would have x squared, and that wouldn't help us substitute for 4x to the 4th. So what we're going to do, and oftentimes with exponentials, it is the exponent. So u is going to be equal to 4x to the 4th. du is equal to 16x cubed dx. And now we're a constant of what we needed as far as our variable was concerned. So I'm going to rewrite this as 1 over 16 du is equal to x cubed dx. And now when we take a look at our substitutions, u is going to be in place of 4x to the 4th, and 1/16 du is going to be substituted for dx and x cubed. So now we can rewrite our integral. So we have the integral of e to the u, and then du, and I'm going to go ahead and put this 1/16 out front. It's just a constant. And now we can integrate. So we have 1/16, and then the integral of e to the u is just e to the u, and then remember our plus c for our constant of integration. And now we need to replace u with our x variable. So we have 1/16 e to the 4x to the 4th plus our constant of integration. We have the integral of ln of x all raised to the 4th divided by x dx. And since we don't know how to integrate ln of x, we're going to go ahead and make that our u. So u is equal to ln of x, du is equal to 1 over x dx. And now we can look at our substitution. So we have u going in place of ln of x. We have du going in place of this 1 over x and this dx. And now we can rewrite our integral. So we have the integral of u to the 4th du. And now we add 1 to our exponent, and we divide by the new exponent. So u to the 5 divided by 5 plus c. And then we replace our u with our x variable. So ln of x to the 5th divided by 5 plus our constant of integration. Alright, so here in this last example I have e and ln of x. So just like I was saying before, we don't know how to integrate ln of x, so that's going to become our u, but also it's the exponent of e, and I also said that normally it's the exponent. So we have u is equal to ln of x, du is equal to 1 over x dx, and now we have u for ln of x, and we have du going in place of 1 over x and dx, and now we can rewrite it as e to the u du. And the integral of e to the u is e to the u plus c, and then we replace it with ln of x plus c. And if you remember, e and ln are inverses of each other, so we could actually rewrite this as x plus c. We could have done that from the start too. So if we take a look at this problem again, we have e to the ln of x divided by x dx. And we could have rewrote this because e to the ln of x is just equal to x as x divided by x dx, which is the integral of dx, or 1 dx if you like, which would be x plus c. The reason I wanted to do it the other way is to show how u substitution works with e and ln. So if you remember the simplifications, this problem was a little bit easier than having to do the u sub, but it's not bad to remember how to do it both ways. And that's all for u sub with e and ln.